The next speaker I have is Andrew Gale from Iris. Again, this is not too dissimilar to some of the technologies that we've been reviewing, but a commercial grade version of one of the motion amplification and motion detection bits of software. And I think it's really important to sort of throw that in the mix, these optical based techniques, as indicated in my short presentation, that you video that is pretty convincing and even a CEO might understand it. And that's an important aspect of consideration when you're trying to communicate that the structure that is worth zillions is just about to fall into the drain. So I won't keep anyone waiting anymore. Andrew, are you ready?
I sure am. I shall try and share my screen.
And you can turn your camera on if you want to, Andrew.
Yep. Okay. All right, so yeah, what we're going to be having a look at here is the motion amplification technology from RDI, which is an American company, and looking at how we can apply that to looking at structures in particular. So without any further ado, what I'm going to do is just start showing you some of the videos that have been captured using the motion amplification technology, and then we'll talk a little bit about the way that it's actually doing it. So the first bit of footage that we've got here at the moment is of a train track. What you see there is what's called motion vectors. So we can have motion vectors that are being drawn anywhere on the video footage that we're capturing, and that's just indicating the the direction of the motion and the amplitude of the motion as the train's passing over that track. Now that video footage that we're looking at there at the moment, there's no actual amplification being applied in that particular part. What we're about to see now is with amplification applied. So now you'll actually see how the track itself is being displaced with the train going over it. It was at normal speed there first off, and now we're just seeing that repeated now with it being slowed down. So those motion vectors we can draw anywhere on the video footage that we're actually capturing. Now we're just looking at a bridge. In this particular exercise, they are more interested in what was occurring the pipe along the bridge there, and again we've got motion vectors that are actually just placed anywhere on the video footage, and they're just tracking how far that's being displaced and in what orientation as the vehicle passes over the bridge. This example here, you've got on a bridge, the lower portion of the video footage is not amplified. The upper video footage is simply where it's been amplified, so we can see the deflection of the bridge as vehicles pass over it. And what we'll see here in a moment too is that we have the ability to actually draw anywhere on that image what's called a region of interest, where the software has the capability to extract an amplitude and a frequency for that matter, to determine how much deflection we're actually got and what sort of frequency you're looking at as far as that deflection is concerned. Now, as I said, those regions of interest, there's a little square red region of interest there in the middle of the bridge, but there's no limit to the number of regions of interest that we draw on a particular image to extract an amplitude and a frequency from that video footage. This next example is on a conveyor system in a mining application, but again, we've got the motion amplification motion vectors that have been put onto that particular image, and we can easily identify where the nodes, the antinodes are. We can extract a spectrum. In this case, you can see from the blue region of interest on the left-hand side. There's an amplitude and frequency being extracted from that location, and the same again from the green region of interest that's been drawn on the conveyor. Now, with any of those amplitude and frequency information that we're extracting, we can do some cross-channel phase correlation, any of those sort of things for any of those locations on that image that we're actually capturing. So just to cover off, what it is that we're doing with motion amplification, we're talking about being able to measure with the video movement that's not visible to the human eye. So, we're talking about displacements that are less than 0.1 of a millimeter. So, in fact, with the system we can go right down to 0.25 of a micron. In fact, as far as minute amounts of displacement are concerned and what we can actually detect in the video. Basically, the way the thing's working is, we're really turning every pixel that we're capturing in the video footage there is like a sensor. So we can extract some meaningful information from every single one of those pixels that we have in the image. And just while we're talking about that for the moment, I mean, the way that I guess the technology is working and being able to extract that meaningful information from the video footage is that we're kind of relying on the fact that there is some contrast to the video that we're acquiring, and it's really looking at what's happening to the light intensity of each of those pixels from one frame to the next as we're capturing the video, and using those changes to help us determine what sort of displacement is actually present there. So that's the way that the technology is actually working and enabling us to extract the the amplitude and frequency of displacements that might be present in the scene that we're videoing. We also apply to that video that we've captured. We also apply we can apply some amplification to it. So when we amplify it, we're really just getting it above that threshold that we would be able to see with our naked eye. So there's a lot to do with being able to visualize the way that the thing's actually displacing under its normal operating conditions, whether it's a structure or a machine that we might be looking at. So what we're really about here is being able to visualize the deflections that might be present. And of course, we can measure and we can quantify any of those measurements that we might want to make, any structure or asset that the camera can actually see. As far as the hardware is concerned, the video camera that we're using, there's nothing particularly special about the video camera itself. It's really more around, I guess, the software and is where all the smarts, I suppose, is as far as processing is concerned. But as far as the hardware is concerned, I mean, there are three configurations, I guess, of the hardware. The standard RSM. When I say standard, it's really a standard frequency range that we're looking at with the RSM system, which is a portable system. The RSMX is more the high frequency. It's a higher speed camera that we're looking at over there. And the IRIS-CM, and CM stands for continuous monitoring. So that's a very recent addition. And the IRIS-CM is really using the standard IRIS-M camera. So looking at the, I guess, the lower to medium frequency range as far as the camera capability is concerned and the frame rate that we can achieve with that system. What we're like for a technical specification point of view, fundamentally we're measuring displacement with the video camera. We're also capable of doing live motion amplification. That is that we can be looking at a live stream of a video that we're acquiring, but applying amplification to that video footage live. So we can see how the thing's deflecting right there on the screen when we're actually looking at it. We have the ability to amplify whatever motion we've detected right up to a maximum of 500 times. So there's plenty of scope for amplifying whatever motion we've detected there to get it to that threshold where we can actually see it with our naked eye. You know, we can slow it down when we're playing it back too, of course. So we've got control over that playback speed when we're reviewing the video footage that we've captured as well. We also have the ability to look at the overall displacement as well as frequency-based motion. We achieve that by applying some bandpass filtering at specific frequencies and only looking at, you know, displacements at that specific frequency, if you like, as opposed to the overall displacement that might be occurring on that particular machine or structure. I mentioned earlier that we can measure right down to 0.25 microns, so we can get down to fairly small amplitudes of displacement that we can detect. The frame rate of the standard RSM system, we can acquire at 180 frames per second in full HD, high definition video footage. And I guess when we look at, that's like a sample rate. So if we were to do an FFT of what we had acquired there, that would give us a maximum frequency on the FFT of the spectrum out to half of that, half of the 180 frames per second. So that's going to be down to 90 hertz that we would see as the Fmax on our spectrum. As opposed to the RSMX, which is the high-speed camera, and it'll go up to a maximum of 1,400 frames per second in HD, which I don't think would be required in the structural health monitoring. I don't think structural health monitoring application. I think most of what we would be looking at there would be with the standard RSM camera. Below that, it's just showing you that, you know, it can in fact, you know, go out to a maximum on the frequency range with the standard RSM camera out to 650 hertz. But to do that, we do need to reduce the resolution of the image that we're acquiring. So no longer HD, we've got less pixels in the image that we're acquiring, but that would enable us to go out to a higher frequency. The measurement that we're making is 2-axis measurements orthogonal to the line of sight. So we'll do at any location on that video footage that we are acquiring, we can extract an X and a Y orientation from any location. And it's a synchronous measurement across the entire image. So that means we can do that cross-channel phase measurement between any 2 points or all of the points that we may have specified for that matter on the structure that we're looking at. Not so fussed about the shaft displacement, but we also have the ability with the continuous monitoring system to do long-term monitoring, and I guess more importantly, triggered recording of critical events. So, for example, if there was a vehicle passing over a bridge, then we can set some trigger points on the video footage that we're capturing based on amplitude of displacement that has occurred, and use that as a trigger to actually acquire and store the video footage that that we're acquiring. And what I'd like to do now is I'm just going to swing over to my monitoring system just so you can see the type of information that we're actually acquiring. So just bear with me while I swing over to my monitoring system. Okay, so what we're looking at now, we're just looking at the motion amplification software here at the moment. We're looking at a live video footage that's coming from this little fan that I've got set up here in my office that we're videoing. And at the moment, there's no amplification or anything like that being applied. So that's just a live feed from the video camera coming through at this point in time. Now, what we've got with a continuous monitoring system is the ability, as I'd mentioned earlier, to set up these triggers. This example that I've got here at the moment is I've just got this region of interest that's been drawn in this top right-hand corner of this this fan that's vibrating here at the moment, and I'm going to use that to trigger the acquisition of the video and the storage of the video footage. So I'm just going to acquire in this live mode at the moment some data. So that's just acquiring from that region of interest that we have drawn on the that video footage, extracted a time waveform, and we've got these trigger points. So I can just click and drag the the trigger point here as a set point to make it acquire and store the video footage, so that we have the ability to set up those triggers in the software. So that's just really showing you the ability to set up those triggers. I'm actually going to that's actually enabled, that trigger at the moment. I'm actually going to set this system to be monitoring automatically. So I'm going to start monitoring. It's going to just clear the buffer, so that's okay. So while it's getting set up to start monitoring, so that's monitoring now, so continuously. Now, in that trigger setup that we were looking at just a moment ago, you could see that it was already above the set point. So immediately, if I go and have a look at the that camera, immediately there is a it's been triggered. The set point has been triggered, and we're actually got some video footage that's actually being stored automatically by the continuous monitoring system. Now, even when we're just looking at this live feed here at the moment in the monitoring mode. The monitoring's actually turned on. We can even while we're just screening on this, looking at this real time, we can just apply a bit of motion amplification. So there's been a bit of motion amplification being applied to it, so we can just see how this thing is actually moving and vibrating around real time. So that's if we just wanted to log on to the system and just see how things are actually deflecting there and then, and that's really just to, I guess, show you what we can see live on the screen. But we've also had a trigger on this one here, and it's extracted the video footage. So I'm just going to launch motion amplification to have a look at what was actually extracted via the system. So now we're in the, if you like, the analysis software. So there's a region of interest that was drawn in that top right-hand corner of that video footage, and of course that's showing us that we've got in the X orientation something like 76 or so microns peak to peak at 23 hertz, and we've got a bit less than that. Oh, it's almost the same, isn't it? 71 microns peak to peak at 23 hertz. So now we're just looking at the video footage that's been extracted from the system. We can press play and see how that thing's deflecting. We can apply those motion vectors to it, see how that's actually moving around at that particular point, and we can go ahead and we can draw any number of regions of interest on this image wherever we like. We can do cross-channel phase measurements with that, so we can get the visualization, we can get the technical data from any of those locations that we might draw on that video footage. So what I shall do is, at that point, I will stop sharing that, and I shall go back to sharing that screen. And at that point, I will throw to questions.
I haven't seen any questions yet, but I'll keep an eye out and welcome anyone to push the unmute button and join in. I guess one of the questions for me is if we've got our own camera systems and our own data feed, like I showed earlier with
John. John.
Yeah.
Now we have switched to this mode, so anyone if they like to ask question, they can simply unmute themselves and ask question. So instead of writing down on the Q&A, so we have now enabled this function. So if anyone who would like, so you can invite people to ask question, unmute themselves and ask the question directly.
Cool. I'm going to get it started. If we've got our own data feed of photograph or image data, can we shove it through your wonderful software and produce cool, super deformed pictures?
Up until the most recent release of the software, it was limited to the camera that's provided with the system. However, in the most recent release, there are additional cameras that are now supported by the software. So what I should do is get you those list of cameras that are actually supported by the software.
Yeah, John, I have a question for so I think the area of motion amplification, I think it has been developed very well and very exciting area. But I think that the next phase for this area is that, I believe that it will be down to the AI technique as well, so that we can make use of the advanced function to look into, the motion recorded, because obviously it's very interesting to see how you amplify the signal, the motion, but you would not want, human eye to look at it and then check, to see whether or not the structure, being monitored, having a problem or not, right? Just from the look of the signal, right? The motion recorded. So I guess it will be down to the area, how we can use AI technique to analyze the data, the motion recorded, so that you can say whether or not structure is okay or not. Just a comment. And also maybe the question would be, at the technology supplier, have you got any feedback from the customer or anyone, who have used this kind of technology to see if they demand anything on the area that I just mentioned, or are they happy with the current status?
Right. I'll take that one if you like, John. So as far as the technology is concerned at the moment, I don't think there has been any work done on the AI side of things and processing and making some determinations directly from the footage. I mean, I guess the first step, as far as the technology is concerned, is providing the ability to continuously monitor a structure and capture the specific events. So if there's been some sort of deviation away from what the normal displacement amplitudes would normally be, it's making sure that we can first capture that interesting footage. And I guess the post-analysis side of things is very much a manual process at this point in time. But that's certainly something that I'd like to feed back to RDI about how we might be able to put some AI analysis into the video footage that we've got the ability to record now.
Yeah, okay, thank you. Yeah, one of the reasons I asked that, because I noticed that the video footage is very, they're very big inside, right? So you can see that, it's just a few minutes, you can see it's just a huge file. and sometimes I find that it's very challenging for human eyes, or if we just look into the footage and then check something, and it's I think quite challenging. Okay, but thank you for that.
Yeah, apologise. I was just trying to line up our next speaker, who I think I haven't given sufficient notice to. But we have not tried to use AI directly in any of our interpretation. We've really used it as a supplementary tool to, almost proof of the squiggly lines that we're getting, and that's really taken me down this path of being more interested in optical motion technologies and the interpretation. I guess the other question to you, Andrew, is around the CM product. I know that lighting and changes in lighting really throw you around if you're trying to do any kind of interpretation. The CM product, I guess, from what you were saying, is really intended to be, you trigger it, look at it, or trigger it and get some analysis out of just these bits. It's not really how has this pipeline changed over the last 5 years. Is that correct?
That's correct. Yeah. Look, I mean, we can obviously record and keep all of those things organized, and you can get a baseline, and I guess, and you can do some comparative measurements. So measurements can be repeated. You can replicate the way in which you've captured the video, but it's not at this point in time. It's not something that is set up to be left in place for a 5-year period, and to, I guess, trend changes that might be occurring over that period continuously. But I mean, this, as I said, this continuous monitoring system is only new, so there would be no reason why the thing couldn't be set up and monitoring over a very, very long period of time. But again, it would be a manual extraction of data at various times during that period.
That's not a major limitation, particularly around our work on trains. That you often have common trains moving over the same bridge at the same sort of times where you can predict them, and the bridge response to a common or a known load is still useful data.